I want to start with a confession. Gravity is the most familiar force in your life, and at the same time, it's the one we understand the least. You feel it every second. It keeps your feet on the ground, the moon in orbit, and the stars glued into galaxies. And yet, when a physicist tells you what gravity actually is, they start waving their hands and changing the subject. That should bother you, because in physics, familiarity is usually a trap. The things that feel obvious are the ones we stop questioning. Gravity is the champion of that mistake. We know how to calculate it. We know how to predict it. But knowing how to calculate something is not the same as knowing what it is. And that's where the trouble begins. One calculation is not understanding. Let me say something that sounds strange, even offensive, to people who love formulas. Physics is not about having answers. It's about refusing to lie to yourself about what you don't understand. Most people confuse these two things. They think if you can calculate something accurately, you must understand it. That's a comforting belief. It's also wrong. We can calculate gravity extremely well, better than almost anything else in physics. We can predict the motion of planets hundreds of years into the future. We can land spacecraft on rocks, flying through space at tens of thousands of kilometers per hour. We can synchronize satellites so precisely that your phone knows where you are within a few meters. If calculation were understanding, gravity would be the most understood phenomenon in science. But calculation is bookkeeping. Understanding is explanation. Those are not the same activity. When you calculate gravity, you plug numbers into equations. Mass here, distance there, curvature here, motion there. The machinery works. The output matches reality. Everyone applauds. But when you stop the math and ask a simple question, what is actually happening? The room goes quiet. Not because the question is childish, but because it's dangerous. Isaac Newton knew this problem better than anyone. He gave us the inverse square law, a stunningly accurate description of how objects attract each other. It worked so well that people immediately assumed he had explained gravity. He hadn't. Newton never explained how two objects pull on each other across empty space. He openly admitted this, made him uncomfortable. He refused to invent a mechanism just to make the story feel complete. He gave the rule and stopped there. That restraint is important. Most people don't have it. They see objects attract each other and immediately imagine invisible strings, forces reaching out, something grabbing something else. But imagination is not evidence. Newton knew that pretending to understand was worse than admitting ignorance. Then Einstein came along and changed the language entirely. Gravity was no longer a force pulling objects together. Instead, space itself could bend, time could slow. Objects simply followed the geometry they were placed in. This was not just clever, it was revolutionary. It explained phenomena Newton's equations couldn't touch. Light bending near massive objects, time running differently in strong gravitational fields, the universe expanding. And it worked. Beautifully. But here's the part people quietly skip over. Einstein didn't tell us why space bends. He told us that it bends and how to calculate the bending. He replaced one mystery with a deeper, more mathematically refined mystery. When you say mass curves space-time, you're not explaining a cause. You're naming a relationship. It's like saying when I turn the knob, the volume increases. That's useful. It's not a mechanism. What is space made of that allows it to curve? What does it mean for geometry to be dynamic? Why should matter influence the structure of reality itself? At that point, the equations stop answering and start staring back at you. This is where people get uncomfortable, because the human mind wants closure. It wants a story. It wants to feel like the mystery is over. So people begin to confuse elegance with truth. They say, the math works, so the explanation must be complete. That's a mistake. Nature doesn't care how aesthetically pleasing your equations are. It only cares whether they match reality. And matching reality does not guarantee understanding reality. A calculator can predict the trajectory of a ball. It does not know what a ball is. We can predict gravity without understanding it. That fact alone should make you suspicious of your confidence. Prediction is pragmatic. Understanding is conceptual. Physics advances when we refuse to treat those as interchangeable. Gravity exposes this confusion more brutally than almost anything else because it is so familiar. You've felt it since birth. You've fallen, stood up, walked, jumped. Gravity feels obvious. That familiarity is precisely why it's dangerous. When something is familiar, we stop questioning it. We accept words as explanations. We accept metaphors as causes. We stop pushing. But the moment you strip away the metaphors, gravity becomes unsettling again. Why should mass attract mass? Why should energy affect geometry? Why should motion follow curvature rather than resist it? These are not philosophical distractions. They are unresolved physical questions. And here's the hardest part to accept. Physics progresses not by answering these questions quickly, but by refusing to answer them dishonestly. Newton didn't pretend to know. Einstein didn't pretend to finish the story. Anyone who tells you gravity is basically understood is confusing confidence with clarity. Prediction without understanding is incredibly powerful. It builds bridges, launches rockets, runs technology. But it is not satisfying because it leaves the central mystery intact. Gravity still works without asking for your intuition's permission, and the equations still run without telling you what's really going on underneath. That silence is not a failure of physics. It's a reminder of what physics actually is. Two gravity does not fit with the other forces. Physics likes unity. Nature, as far as we can tell, prefers simple rules that apply everywhere. When something refuses to fit, it's usually not a small problem, it's a crack in the foundation. Gravity is that crack. We have 4 fundamental interactions in nature. 3 of them behave like good citizens. Electromagnetism, the strong force, the weak force. They all submit to the same basic framework, quantum mechanics. They are described using particles, probabilities, fields that fluctuate, and interactions that happen in discrete, measurable ways. Gravity refuses to cooperate. This isn't philosophical resistance. It's mathematical rebellion. When physicists try to treat gravity like the other forces when they try to quantize it, the same way the equations break, they don't just get complicated. They blow up. Infinities appear where finite answers should be. Predictions stop meaning anything. And that's not because physicists are careless. It's because the framework itself stops working. This is deeply unsettling because quantum mechanics is not optional. It governs everything else in the universe. Atoms, light, chemistry, biology, technology. If gravity cannot be expressed in that language, then either gravity is fundamentally different or our understanding of quantum mechanics is incomplete. There is no comfortable third option. People sometimes downplay this problem by saying things like, well, gravity is just very weak. That sounds reasonable until you think about it. Weak forces don't refuse to be quantized. Weak forces just produce small effects. Electromagnetism can be extremely weak in some contexts, yet quantum theory handles it perfectly. Weakness is not the issue. The issue is structure. Gravity doesn't act like a force transmitted through space. In Einstein's formulation, gravity is the structure of space, and that creates a fatal conflict with quantum theory, which assumes space is a fixed background where things happen. Quantum mechanics treats space as a stage. General relativity treats space as an actor. You can't have both without rewriting the script. This is where gravity exposes a deeper problem. Our most successful theories are built on incompatible assumptions about reality. Quantum mechanics assumes uncertainty is fundamental. Positions, energies, and outcomes are probabilistic. You don't get exact answers, you get likelihoods. General relativity assumes geometry is smooth and deterministic. Given the distribution of matter and energy, space-time curves in a precise way put uncertainty into geometry, and geometry stops behaving like geometry. Distances fluctuate. Time loses its meaning. Cause and effect become fuzzy. That's not a technical inconvenience. That's a conceptual collapse. Physicists have tried to patch this problem for decades. They've invented mathematical frameworks, hypothetical particles, extra dimensions, vibrating structures smaller than anything we can observe. Some of these ideas are elegant, some are clever, none are confirmed. That alone should tell you something important. If gravity fit naturally into quantum theory, we would have unified it already. The mathematics would settle down. The infinities would cancel. The predictions would stabilize. They don't. This tells us that gravity is not just another force waiting to be folded in. It's pointing at something deeper, something we don't yet know how to describe. Here's where intellectual honesty matters. It's tempting to say, we just need better math, as if this were a homework problem. But history shows that when equations refuse to cooperate for this long, the issue is usually not technical skill. It's conceptual misunderstanding. Newtonian mechanics failed not because the math was sloppy, but because time and space were assumed to be absolute. Einstein fixed the problem by changing the assumptions. Something similar is likely happening here. Gravity's refusal to fit may be telling us that space, time, or even causality itself is not what we think it is. And until we're willing to question those assumptions, the equations will keep punishing us. Another uncomfortable truth: we don't observe gravity the way we observe the other forces. We can isolate electromagnetic interactions. We can shield them, turn them on and off, measure individual exchanges of energy. We can't do that with gravity. Gravity affects everything, always. You can't block it. You can't neutralize it. You can't switch it off to see what happens without it. That universality is beautiful, but it's also a problem, because it means gravity may not be an interaction in the usual sense. It may be a consequence of something more fundamental, something built into the structure of reality itself. If that's true, then trying to quantize gravity like the other forces may be like trying to quantize temperature. Temperature isn't a particle, it's a collective behavior. Gravity might be similar. This possibility terrifies neat theories because it suggests we've been asking the wrong question. Instead of how do we quantize gravity, the real question might be, why does gravity emerge at all? And that's a much harder question. Gravity doesn't fail to fit because physicists are incompetent. It fails to fit because it may not belong in the same category as the other forces. That mismatch is not a flaw in nature. It's a warning sign for us. When a theory works everywhere except one place, the problem is usually not the place. It's the theory. Gravity is not being stubborn. It's being honest. And until we are equally honest about what we don't understand, gravity will continue to sit outside our theories, quietly reminding us that consistency is not the same as comprehension. 3. Space itself is not as solid as we think. Most people imagine space as nothing, an empty container where things happen, objects move through it, forces act across it, but space itself just sits there politely doing nothing. That idea is wrong. It's not just slightly wrong. It's fundamentally misleading. Einstein shattered the idea that space is passive. In general relativity, space is not a backdrop. It stretches, compresses, twists, and responds. Time does the same. Together, they form something dynamic, something that reacts to mass and energy. This already stretches intuition, but it still tempts us into a quiet assumption that space, even if it bends, is still something solid underneath, smooth, continuous, well-defined at every point. That assumption may be the real problem. Because when physicists try to look closely, really closely, space starts to misbehave. At very small scales, quantum mechanics doesn't allow sharp definitions. You can't specify an exact position without uncertainty. You can't define energy precisely without blurring time. Everything fluctuates. If space itself is subject to quantum rules, then space cannot be perfectly smooth. It must jitter. It must fluctuate. It must sometimes fail to behave like geometry at all. And the moment you accept that, the idea of curvature becomes slippery. Curvature assumes something continuous to bend, but if space is grainy or discrete or emergent, then what exactly is bending? What does curvature even mean? This is where gravity quietly dismantles our assumptions. We talk about space as if it were a thing, but we've never observed space directly. We observe relationships, distances between objects, durations between events, motions relative to other motions. Space may not be a substance at all. It may be a bookkeeping system we invented to organize those relationships. If that's true, then gravity isn't bending a thing. It's altering relationships. And that's a very different statement. Imagine temperature. Temperature feels real. You feel hot or cold. But temperature is not a fundamental entity. It's an average behavior of countless particles moving around. Remove the particles, and temperature disappears. Space might be similar. What we experience as space could be an emergent property of something deeper, something that only looks geometric when viewed from far away, just like a crowd looks smooth until you zoom in and see individuals. At large scales, space behaves nicely, it curves smoothly, Einstein's equations work, everything looks continuous. At small scales, that smoothness may be an illusion, and gravity might be the clue that gives it away. This idea makes people uneasy because it removes solid ground literally. If space is not fundamental, then neither is location, neither is distance, neither is even time in the way we imagine it. And yet, physics keeps pointing in this direction. Whenever we push gravity into extreme situations near black holes, near the beginning of the universe, at scales where quantum effects matter, the concept of smooth space-time starts to fail. Singularities appear. Equations break. Predictions stop. That failure is not random. It's systematic. It suggests that space-time, as we currently understand it, is a large-scale approximation. Useful, accurate, but not ultimate. Here's the uncomfortable implication. Gravity may not be something happening in space. Gravity may be a signal that space itself is not what we think it is. This flips the usual question upside down. Instead of asking, what causes gravity? We may need to ask, what causes space? And that's a much more dangerous question. Because once you ask it, familiar language stops helping. You can't rely on shapes, curves, or dimensions if those are the very things under investigation. At that point, physics becomes less about visualization and more about consistency. You're no longer trying to picture reality. You're trying to describe it without contradiction. Feynman was very clear about this danger. He warned repeatedly against confusing mental pictures with truth. The universe does not care whether you can imagine it. If space is emergent, then gravity might be a statistical effect, a large-scale consequence of microscopic rules we don't yet understand. Just as pressure emerges from molecular motion, gravity could emerge from deeper interactions that don't look gravitational at all. This would explain why gravity behaves so differently from the other forces. It wouldn't be a force in the same category. It would be a collective phenomenon masquerading as geometry. And that would explain why attempts to quantize gravity fail so stubbornly. You don't quantize averages. You quantize the underlying constituents. Trying to quantize gravity directly may be like trying to quantize waves without knowing about water molecules. The waves are real. The math works, but the explanation is incomplete. This idea doesn't solve gravity. It makes gravity harder, but it makes the difficulty meaningful. Instead of treating gravity as a broken piece of quantum mechanics, It treats gravity as a hint that our picture of reality is layered, that what we call space is not the base layer. And here's the key point that people miss. Not understanding space is not a philosophical embarrassment. It's a scientific opportunity. Every time physics has been forced to question what seemed obvious time, simultaneity, motion, matter, it has made enormous progress. Gravity is forcing that kind of reckoning again, not because it's mysterious, but because it's familiar enough to trick us into thinking we already understand it. Space feels solid. Gravity feels obvious. That confidence is exactly what's slowing us down. Gravity is not just bending space. It's bending our assumptions about what space even is. 4. We confuse models with reality. Let me warn you about one of the most dangerous habits smart people develop: falling in love with their own explanation. A model is a way of thinking. It's a tool. It's a mental shortcut that helps you calculate, predict, and organize observations. It is not the thing itself. And the moment you forget that difference, you stop doing physics and start doing mythology. Gravity suffers from this confusion more than almost anything else. We say gravity is a force. Then we say it's curvature. Then we say it's geometry. Each time, the language feels more refined, more sophisticated. And each time, people quietly replace curiosity with comfort. That's a mistake. When Newton described gravity as a force, people imagined invisible pulls acting across space. It felt intuitive. Two masses attract each other. Simple story. The math worked, so the picture stuck. But Newton never said the picture was real. He knew it was a placeholder, a convenient fiction that let calculations proceed without pretending to explain the mechanism. Later, when Einstein described gravity as curved space-time, people switched metaphors. Now they imagined rubber sheets, heavy balls, dents and slopes. That felt deeper, more geometric, more fundamental. But again, the picture became mistaken for reality. The rubber sheet analogy is not gravity. It's a teaching device. It borrows gravity to explain gravity, which should already make you suspicious. It's a visual crutch, not an explanation. And yet people cling to it because it gives the illusion of understanding. This is where physics becomes psychologically dangerous. A good model works so well that you forget it's a model. You stop asking where it breaks. You stop asking what assumptions are hidden inside it. Gravity hides behind beautiful mathematics and clean metaphors. That makes it harder to see the cracks. Here's the key point most people miss. Every model makes assumptions. Some are explicit, some are buried so deeply you forget they're there. Newton's model assumes space and time are absolute. Einstein's model assumes space-time is smooth and continuous. Quantum mechanics assumes probabilities are fundamental. These assumptions are not facts. They are starting points. Gravity forces us to confront the possibility that our starting points are wrong. When you say space bends, you are assuming space is the kind of thing that can bend. When you say objects follow geodesics, you are assuming geometry exists independently of what's being measured. Those assumptions work until they don't. The moment you push gravity into regimes we haven't tested deeply inside black holes, near the beginning of the universe at quantum scales, the models start to contradict themselves. And instead of questioning the models, people often defend them. They say things like, the math will work out eventually, or we just need more data, or it's a technical issue. Sometimes that's true. Often it isn't. History is brutal about this. Physics advances not by polishing old models forever, but by recognizing when they've outlived their usefulness. Classical mechanics wasn't wrong. It was incomplete. Newtonian gravity still works beautifully for most purposes. Einstein didn't destroy it. He showed where it breaks. The same may be happening now. Gravity may be telling us that space-time itself is a model, an extraordinarily successful one, but not the final description of reality. That idea scares people because it threatens the sense of solidity we get from geometry. Distances, durations, coordinates. These feel objective, stable, real. But feeling real is not the same as being fundamental. Consider sound. Sound feels real. You hear it, you measure it, you analyze it. But sound is not a fundamental thing. It's a pattern of pressure variations in a medium. Remove the medium, and sound disappears. Space may be similar. What we call space might be a convenient way to summarize relationships between events, not a substance that exists independently. If that's true, then gravity isn't bending space, it's changing relationships. And our models, which treat space as a thing, may be subtly misleading us. This is why Feynman was so insistent about intellectual honesty. He warned against mistaking the description for the described. The map is not the territory, the equation is not the phenomenon. A theory can be correct and still incomplete. It can work perfectly and still be hiding a deeper truth. Gravity punishes anyone who forgets this. Because gravity is not impressed by elegance. It doesn't care if your equations are beautiful. It doesn't care if your metaphors are intuitive. It only cares whether your predictions match reality, and even then, it refuses to tell you why they do. That silence is important. It means nature is not obligated to explain itself in human terms. It doesn't care whether we find the story satisfying. Our job is not to defend our models. Our job is to test them, stress them, and abandon them when they stop making sense. Gravity is forcing us toward that uncomfortable edge again. Not because our models are useless, but because they may be too successful to question easily. The danger is not ignorance. The danger is thinking your explanation is reality itself. Gravity keeps reminding us of that, quietly and relentlessly. And the sooner we accept that our best descriptions are provisional, the sooner we can move closer to whatever is actually going on underneath. 5. We don't know why mass exists at all. Here's where gravity stops being a problem about forces, fields, or geometry and turns into a much more uncomfortable question. What exactly is mass, and why does it exist in the first place? Most people think mass is obvious. Things have weight. Heavy objects resist being pushed. Light objects don't. End of story. But that confidence evaporates the moment you try to explain mass instead of using it. In physics, mass plays two very different roles, and the fact that they turn out to be the same number is one of the deepest clues we have and one we still don't fully understand. There is inertial mass. How much an object resists acceleration. Push harder, it speeds up more slowly. That's inertia. And there is gravitational mass. How strongly an object responds to gravity. Heavier objects feel stronger gravitational effects. Experimentally, these two are identical. To extraordinary precision, they are the same. Einstein built general relativity on that fact. But here's the catch. Physics does not explain why they are the same. It assumes they are. That assumption works brilliantly. But again, assumption is not explanation. Why should resistance to acceleration be linked to how something curves space-time? There is no obvious reason. We treat it as a fact of nature because nature keeps agreeing with it, but agreement is not understanding. Now let's make things worse. In modern physics, mass is not fundamental in the way people think. Many particles do not have mass inherently. They acquire it through interactions, through mechanisms, through fields. That tells you how mass appears, not why the universe allows such a property to exist at all. And gravity doesn't care how mass arises. It responds to it regardless. Anything with energy, momentum, pressure, anything at all gravitates. This should bother you. Gravity is sensitive not just to mass, but to energy itself. Light bends in a gravitational field. Radiation contributes to curvature. Even empty space, if it has energy, affects gravity. So what is gravity really responding to? not stuff in the ordinary sense, not just particles sitting around. It responds to something more abstract, the bookkeeping of energy and motion. This is where explanations start to wobble. We say mass curves space-time, but energy also curves space-time. Pressure curves space-time. Stress curves space-time. Things that don't even feel like objects curve space-time. So the phrase, mass causes gravity, is already a lie of convenience. It's energy in all its forms that matters. And we don't have a deep explanation for why energy should influence the structure of reality itself. Why should motion affect geometry? Why should pressure warp time? Why should the mere presence of energy dictate how distances behave? Those are not small questions. They go to the core of what we mean by existence. Now consider this. Mass is measured relative to something else. You only know how massive an object is by how it behaves when you interact with it. Push it, accelerate it, compare it to another mass. Mass is relational. Gravity, too, is relational. You only feel it relative to something else. A planet, a star, a field. That parallel is not accidental. It suggests that mass may not be an intrinsic property in the way we imagine. It may emerge from interactions, from relationships, from deeper dynamics we don't yet see. If that's true, then gravity is not reacting to a substance. It's reacting to structure. And structure is not something we've fully defined. This is why gravity remains so stubborn. It sits at the intersection of two things we don't fully understand: mass and space-time. We build equations that connect them. The equations work, but the connection itself remains unexplained. People sometimes think discovering a mechanism for mass would automatically explain gravity. That's optimistic. History suggests the opposite. Every time we've explained one layer of mass, gravity has simply followed along without revealing its secrets. The problem isn't that mass exists. The problem is that gravity treats mass, energy, motion, and pressure as fundamentally the same kind of thing. And our intuition does not. We think of objects. Gravity thinks in terms of accounting. That mismatch is telling us something important. It suggests that gravity is less about pulling things together and more about how the universe organizes information about energy and motion. That's not poetic language. It's an admission that our everyday concepts are inadequate. We don't know why mass exists. We don't know why it has the gravitational effect it does. And we don't know why inertia and gravity are linked so perfectly. What we do know is that pretending these questions are settled slows progress. Feynman was ruthless about this kind of honesty. He had no patience for explanations that merely renamed mysteries. Saying the Higgs gives mass explains a mechanism, not a reason. Saying mass curves space-time explains a rule, not a cause. Gravity doesn't fail because we lack equations. It fails because it exposes how many concepts we treat as fundamental without understanding why they are allowed to exist at all. That's not a weakness of physics. It's a reminder of how much deeper the universe goes than our current language allows. 6. Nature does not owe us intuition. One of the most subtle traps in physics is the belief that understanding should feel intuitive. People think that if something is truly understood, they should be able to picture it clearly in their head, explain it with a simple analogy, or relate it to everyday experience. That expectation is not just wrong, it actively blocks progress. Gravity exposes this weakness mercilessly. From the moment we're born, gravity feels obvious. Things fall down. Heavy objects feel heavier. The ground stays under our feet. Our intuition is trained on these experiences long before we ever encounter equations. But intuition is not a guide to truth. It's a guide to survival. Your brain evolved to throw objects, catch them, and avoid falling. It did not evolve to reason about space-time, quantum fields, or curved geometry. Expecting your intuition to scale up to fundamental physics is like expecting your eyesight to detect radio waves. Gravity violates intuition in every serious formulation we have. Newton's gravity involves action at a distance. Objects influence each other instantly across empty space. That offended intuition even in Newton's time. He didn't like it. He accepted it only because the math worked and the predictions were right. Einstein tried to fix that discomfort by eliminating force altogether. Now, gravity wasn't pulling anything. Objects were just moving along the natural paths of curved space-time. That sounds more intuitive until you ask what space-time actually is. Curved time, warped distance, different clocks ticking at different rates depending on location and motion. These ideas don't align with everyday experience at all. We accept them not because they feel right, but because experiments demand it. And even then, our intuition fights back. We want to imagine space-time as a surface. We want to draw grids and curves. We want pictures. But pictures are lies we tolerate for convenience. The universe is under no obligation to fit inside your mental imagery. Gravity is especially cruel in this respect because it works perfectly while refusing to explain itself in intuitive terms. It doesn't give you a mechanism you can point to. It gives you relationships that must be accepted whether you like them or not. People often say, "I can't understand gravity because I can't visualize it." That's not a failure of intelligence. It's a misunderstanding of what understanding means. Understanding in physics does not mean comfort. It means consistency. It means you can apply a framework without contradiction and predict outcomes reliably. Your inability to visualize a curved four-dimensional space-time does not make it false. It makes your brain limited. This matters because when intuition becomes the standard, people start rejecting correct theories for emotional reasons. They say, "That doesn't make sense to me," as if the universe asked for their approval. Gravity doesn't care. It bends light whether you like the explanation or not. It slows clocks whether you believe it or not. It creates black holes whether or not you find them intuitive. Every major advance in physics involved abandoning intuition. Time was absolute until it wasn't. Space was fixed until it wasn't. Particles were solid until they weren't. Determinism ruled until probability took over. Each step forward felt wrong at first. Gravity sits at the center of this discomfort because it forces us to confront how deeply intuition misleads us. The closer we look, the less gravity resembles anything from daily experience, and yet people keep trying to make it make sense by squeezing it into familiar stories. That urge is understandable. It's also dangerous. When intuition becomes a requirement, progress slows. Scientists start choosing theories that feel nice instead of ones that work. Feynman warned constantly about this. He emphasized that nature is not classical, not visual, not obligated to be explainable in ordinary language. The job of physics is not to satisfy intuition. It's to describe reality accurately. Gravity teaches this lesson better than any textbook. It works in ways we cannot picture. It connects concepts that feel unrelated. It behaves consistently while remaining conceptually opaque. That's not a flaw. That's a signal. It means the universe is deeper than our evolved instincts. And that understanding requires discipline, not comfort. If gravity made intuitive sense, we would have solved it centuries ago. The fact that it doesn't is not an embarrassment. It's an invitation to think more carefully, more humbly, and without demanding that reality explain itself in terms we find pleasing. Nature does not owe us intuition, and gravity is its most effective reminder of that truth. 7. Admitting ignorance is the engine of discovery. There is a strange pressure in science that rarely gets talked about. The pressure to sound like you understand more than you do. People want clean stories, final answers. They want to believe the big problems are either solved or just one clever idea away from being solved. Uncertainty makes people uneasy. Gravity does not cooperate with that desire. After centuries of work, gravity still sits in an uncomfortable position. It works perfectly where we can test it, and collapses conceptually where our theories overlap. That is not a temporary inconvenience. It is a sign that something fundamental is missing. The dangerous response to this situation is confidence. When scientists or communicators pretend gravity is basically understood, they are not being optimistic. They are being dishonest. They are smoothing over ignorance instead of confronting it. Feynman had no patience for that attitude. He insisted that the first step in discovery is to admit what you don't know, not quietly, not defensively, openly and precisely, because the moment you pretend a question is answered, you stop looking for better ones. Gravity survives every attempt to be over-explained. People say, it's curvature, as if that ends the discussion. But curvature is a description. It tells you how things behave, not why they behave that way. People say, it's geometry, as if geometry were self-explanatory. But geometry is a human invention, a language we use to describe relationships. Nature does not owe geometry any loyalty. People say quantum gravity will fix it without being able to say what quantum gravity actually is. These are not explanations. They are placeholders. And placeholders are useful only if you remember they are placeholders. Admitting ignorance is not weakness. It is precision. It tells you exactly where understanding ends and speculation begins. It draws a clean boundary between what works and what we only hope works. Every major leap in physics began with someone saying, this doesn't make sense, and I'm not going to pretend it does. Newton admitted he didn't know how gravity acted across space. Einstein admitted classical space and time made no sense in light of experiments. Quantum pioneers admitted determinism had failed. Progress followed honesty. Gravity is waiting for the same treatment. Not more confidence, not more metaphors, not more declarations of inevitability. It requires patience with confusion. It requires the discipline to say, we can calculate this, but we do not yet understand it. That sentence is uncomfortable. It doesn't sell certainty. It doesn't sound finished, but it's true. And truth, not comfort, is what moves science forward. There is a temptation to believe that future theories will make gravity intuitive, simple, obvious. History suggests the opposite. Each deeper theory has made reality stranger, not friendlier, more abstract, not more familiar, more precise, not more comforting. Gravity will likely follow that pattern. And that means the real breakthrough won't come from someone who claims to finally understand gravity. It will come from someone who is honest enough to say, here is exactly where our understanding breaks. Gravity is not unsolved because we lack intelligence. It is unsolved because the universe is under no obligation to fit inside our current concepts. Admitting that is not surrender. It is the starting point. Gravity has been teaching us this lesson all along. The question is whether we are willing to listen. Let me end this the only honest way. Gravity is not mysterious because it is complicated. It is mysterious because it is familiar enough to hide its own ignorance. We grow up feeling it, trusting it, using it, and we mistake that intimacy for understanding. We don't understand gravity because we learned to calculate it before we learned to question it. We built equations that work and stories that comfort us, and then we stopped asking what those stories are made of. We call it force. We call it curvature. We call it geometry. Each name explains behavior, not cause. And gravity tolerates all of them while remaining silent about what it actually is. That silence is not a failure of science. It is the edge of science. Every time physics has advanced, it has done so by recognizing the limits of its own language. Time was not absolute. Space was not fixed. Matter was not solid. Certainty was not guaranteed. Gravity is the next place where our language runs out. It may turn out that gravity is not a force, not a field, not even a fundamental interaction at all. It may be an emergent effect, a bookkeeping rule, a shadow cast by deeper principles we haven't learned to describe yet. Or it may demand an entirely new way of thinking, one that makes our current debates look naive in hindsight. The honest position is not to guess which outcome will win. The honest position is to admit we don't know. Richard Feynman understood this better than most. He was comfortable living at the boundary between knowledge and ignorance. He trusted that confusion, when handled carefully, is not a weakness but a compass. Gravity remains unresolved, not because we are careless, but because we are standing at that boundary again. And that is exactly where real understanding begins.